features slash ideas in order to write a program that implements this sorting algorithm in Snap. So the first big idea that we have is that we're going to need two loops, one of which has to be nested inside the other. Now, why do we need two loops? Well, the first one, which we call the outer loop, this sort of darker yellow one here, does this whole repeat business, right? So repeat the 3 steps below for the length of list times. That's what the outer loop is actually doing. But we also need a second loop, this inner loop here, that finds the position of the smallest score in our list. The second loop has to be nested, right? So this light yellow loop is inside this darker yellow loop because we need to make sure that every time we run the outer loop, every time we do the repeat, we're doing step 1, right? Because that's what the inner loop is doing. The inner loop is responsible for step 1. And so we need to make sure that step 1 runs every time we repeat. Now, a common mistake that people forget to include the outer loop, right? So people forget that this darker yellow outer loop here has to be included. Now, why is that a problem? Well, a program that's missing the outer loop will insert the smallest score from the original list to the end of results list. That's good, that's what we want to happen. But then the program will just stop, right? That's not what we want. There are still a bunch of scores in scores list that need to be added to results. So this outer loop here, oh, there's my mouse. This outer loop here is responsible for making sure that every single score in scores list is taken into account. A second big idea is that we need to find the position of the smallest score. So what we actually need is we need the smallest element code pattern from the tutorials, but we need to modify it to keep track of the position of the smallest element, not the value. Now, we need this because this lets us insert the smallest score at the end of the results list. So at first, this is going to be the smallest value, and then we're going to see that, okay, this 1 at position 2, this is going to get inserted, then the next smallest score, and this one here, and etc., etc. You already saw the high-level algorithm for finding the smallest element in the tutorial. In a nutshell, it's a repeat loop that checks each value in scores list, and each time it finds a score smaller than what is in the smallest scores variable, it updates itself. A common mistake here is that people use exactly that code pattern instead of adjusting it to find the position of the smallest element. So again, let's ask the question, why do we care about the position? That's because if the list contains a duplicate of a score, for example, it contains a 1 and another 1, then the position will tell us exactly which number we are talking about. And this is exactly why programming languages like Snap require that when we delete an element from a list, we need to provide the position of that element being deleted. That way, if there are 2 elements in a list that have the same value, there won't be any confusion in the computer's mind or our own about which thing to delete. Now, a third big idea is that we need a second list to keep track of the currently sorted scores. And in this case, we've called that list results list. Now, this list will eventually contain all of our sorted numbers. And notice that this list is constantly growing. Each time we go through the outer repeat loop, this sort of darker yellow loop out here, we append the currently smallest score to the end of results list. Now, a common mistake is to forget to use this second results list. But what would happen if we did? Suppose your program instead inserts the smallest value at the end of the original scores list. So this is the list we start with. We go through our whole process, we find that this one is the smallest, we delete it, and instead of adding it to another list, we append it to the end of our original list. So now instead of 5, 1, 4, 1, 3, we have 5, 4, 1, 3, 1, right? This 1 is still in the list. So there's a problem with this approach. And the problem is that this outer loop up here is designed to run for as long as there are values in scores list. If we use this approach and we keep just appending a value, what's going to happen is the outer loop will never stop running, right? This loop out here, this one, won't stop because there will always be 5 values in this list, which is an issue. We don't want our programs to run forever, right? It's true. We delete this value here, so you would think our value count goes down to 4. But when we append the value again, we go back up to 5, and we never actually change that count from 5. So the takeaway here is that though you actually can program an algorithm that does this, that appends values, it doesn't make sense in this context because we don't want our outer loop to run forever. We need a second list to keep track of our currently sorted scores. Now, the final big idea is that we need to remove the score from scores list each time it's added to results. Now, a common mistake that programmers make is that they forget to do this removal. And why do we have to remove the score? Well, if we didn't remove it, our program would always just find that score when it looked for the smallest one. And so it would keep adding that score to the end of results list, like here. If we forgot to remove the 1 here, then it would just keep going, and it would keep adding that 1 forever and ever and ever, right? So we have to remove it in order to make sure that it keeps finding the next value we need. And that's it. Those are the big ideas. That's the sorting algorithm. And now, after all of that, you're ready to learn how to implement it in Snap. So now that we've talked about the high-level algorithm of how to sort a list